Okay, it's an exam focus. So today I put here the Thermodynamics 2019 semester 2 B1 and B2 because even though only B1 joining today, but this is applicable to B2 as well. The same like in the first revision, only B2 joined, you were not there. Okay, so that's why you have to go through the video and all. And let me put important things for today. Okay, understanding entropy. Actually, we have done this. Okay, we have done this. So this is very important, and I hope you have the videos with you, and even some notes maybe, and you have the text also I passed to you in the beginning of these sessions. I mean thermodynamics class. Understanding entropy. So under understanding entropy, yeah, there are several things we should know. There is one notes, and we have done about further understanding entropy. Entropy further understanding. There were slides all. So this one, I believe you have this. Okay, this helps entropy further understanding. Okay, and here mainly you can see about the efficiencies, Kelvin-Planck statement, okay, and about this kinematics, and not all the thermal energy available is not producing mechanical work, so there is loss of availability of thermal energy for mechanical work that reflects the entropy and all. We have discussed something. Okay, and I believe you have a little video on this. Okay, so this is a very important knowledge you should be looked into. Even in your classroom lessons, we have learned entropy. In your classroom lessons, I can clearly remember, we have learned, and even we learned the definition of entropy using the property tables. Yeah, we have learned how this delta S can be delta Q by T or delta H by T. We have learned these things, even in your class. And there is another note here. Okay. Because this is further understanding. Before that, there is another note, understanding entropy using thermodynamics property tables. Okay, so here, definitely there is the video related to this. because this all notes based on the records, okay, Zoom recordings. So while in the Zoom session, we have developed this notes. So you take a property, take the property table. So here pressure at 1.5, this is for saturation. So we have proved this one, we have proved this. And then about the SFG, so we came to this, okay. So you have to go through this. I'm not going to go through this right now, okay. Understanding entropy, and you have to look into the value. Further understanding afterwards, understanding and further understanding. Some entropy applications, okay, Bhutan? So based on this topic, based on this slides and the records, there will be an exam question, okay? There will be an exam question. And some more. Give me a second, Buddha. Please be patient. Please be patient for a while. Okay. And there is one more diagram related presentation. I'm looking into that. Give me a second. Okay. Don't worry, let me find it afterward. Okay. Good. Okay. Yes, this one. Okay, this one already here. So you have to go through this. You have to go through this, and I'm looking for one more. Yes. Yes. And there is another note here. I just extract. Closest inequality statement, even closest inequality, that should be somewhere in this presentation as well. Okay, closest inequality. That should be. Yes, greater than, you can see. See closest inequality. Okay, so there is another detailed one for this. Closest inequality. 3 slides you can see. Also, there should be corresponding videos. Don't worry about the videos. You have to understand this. So these are very important things. So there will be questions about, not to say very difficult questions, but understanding entropy. Okay. There will be questions. Okay. Related to some applications possible. Okay. Related to some applications. Yes. Okay, good. And I'm going to put this closest inequality statement again, equality one. Okay. Let me put it. Delta Q by T. Okay. Yeah. Where S is entropy, so this is Clausius statement for reversible processes. So T is temperature, okay, in Kelvin. So even we can say this as TK. K stands for Kelvin. Okay, T is temperature in Kelvin. Q, so here I put delta Q is heat transfer. Okay, Q. So the unit of entropy is, so unit of heat transfer in joule or kilojoule per Kelvin. This is capital K. Okay, so for 1 kg, we call specific, means per unit mass. Entropy then, joule per kilogram per Kelvin. Okay, or joule per Kelvin, or even you can be kilojoule per Kelvin. Kilojoule. Or this can be kilojoule per kilogram per Kelvin. Okay, kilojoule per kilogram per Kelvin. Yes. And this is about entropy. And for this is for reversible. So reversible process, no friction, and always there is a quasi-equilibrium. Okay, there is an equilibrium with the surrounding, means any heat transfer, the temperature difference, there should be a temperature difference should be very little. Okay, so we have learned about quasi. There should be, you have learned about this quasi equilibrium. Okay, equilibrium like, see, quasi equilibrium. So you can see equilibrium looks like in balance, but it is not so. Quasi means. So you can see this delta S for inequality, heat transfer delta Q, temperature Tk. So entropy rise delta S is delta Q by Tk. Okay, for equilibrium. If not, this is the one greater than delta Q by Tk. Okay, so that's the situation. You should know this. See, greater, not in a balance, means the surrounding and the system, the temperature difference is not negligible, means system is not in equilibrium with the surrounding. Yeah. So this is good. Again, you have energy into the system, work out loss. Okay, Q in minus W net energy balance is Q loss. So then you can have an efficiency term. Efficiency term is here. Okay. So work out divided by energy in. Okay, good. So you have to go through this Bhutan and there will be a little question out of this knowledge. There will be a little question out of this knowledge. So I will again explain you about isentropic, means constant entropy process. Constant entropy means unchanging entropy. Or we call isentropic, means isoentropy, isentropic. So definitely, so here you can see this is for a thermodynamic process. Okay, so isentropic process. Isentropic process. No heat transfer. Okay, no heat transfer, constant entropy, because since if delta Q is 0, delta S also must be 0. Okay, 0 so must be delta S, means delta S is 0. Hence delta S is 0 as well. So let me look into the definition here. So for isentropic processes, you can say this equilibrium, or this is reversible processes. Okay, reversible processes. So delta S can be written as delta Q by K. Okay, delta S is equal to delta Q by K. Equal to, okay. So isentropic, no heat transfer. And see, friction is also have to be zero because these are equilibrium processes always. Quasi-equilibrium process. Okay. Equilibrium. We call this reversible. Okay. So, reversible process. No friction. Okay. No friction. Yes. So, because it's reversible, no friction. No heat transfer is called adiabatic. Okay. See, no heat transfer for isentropic because when delta S means no entropy rise, no heat transfer. So for sure, heat transfer is zero. So for reversibility, even no internal generation of heat. So no friction. Okay, so no friction is one condition. And no heat transfer is the other one. Okay, so reversible adiabatic. Okay, reversible adiabatic. So no friction, no heat transfer. Okay, so no friction related to one aspect of reversibility. One aspect of reversibility and very small temperature gradients means always let's say like quasi zero temperature gradient means no temperature difference in heat transfer. Reversible means heat transfer is possible. Okay, heat transfer is possible, but gradient is almost very minimal. Okay, quasi. So another word may be here instead of this. I will put minute means it's a very small temperature gradient. So the system doesn't feel this heat transfer. So equilibrium process. Reversible means no friction is one. This is another. So this is reversibility related to heat transfer. Because the friction generates heat. Okay, and that heat is, of course, because of overcoming the frictions. So that heat has no use for the work done. Okay, there is a work loss for that generation of heat. So there should be no friction. Okay, so negligible temperature gradient in heat transfer, minute or negligible. So it may be longer time taking process. Okay, so quasi-equilibrium process. But the issue is, yes, quasi-equilibrium or reversible process. But when it comes to isentropic, means delta S, constant entropy has no increase or change of S. So delta S 0 means delta Q is 0. And here, this equal sign, okay, equal sign here, stands for reversibility. Okay, equal sign stands for reversibility. Okay, so to understand this, you have little enough time because exams are not yet, the dates are fixed, but sure there will be exams. Yeah, so you have time to comprehend this. Okay, so delta Q is 0. So only being 0 is not enough, because if you take this Clausius inequality statement, see, delta S is greater than or equal. Equal stands for reversibility. So if not reversible, delta S can be more than 0 even though delta Q is 0. Okay, so equal stand for reversibility. That's why this is a reversible process. Okay, so I'll take a new slide here. So even you can put this as a reversible process. Reversible process. Nice. Okay, reversible process. Reversible process. Because of this, irreversibility always increasing the entropy. So reversibility is important. Okay, so reversible, that is one thing. Adiabatic, no heat transfer is one thing. So two conditions. I put 1, no heat transfer. 2, reversible. Delta S equals 0. If the process is reversible, is reversible. That's a condition. So reversible. Yes. So delta Q is 0 means adiabatic. Means no heat gain, no heat loss. Okay. Adiabatic. So if it is reversible and is adiabatic, then no delta S increase means isentropy. That's why process with no heat transfer is called adiabatic, and adiabatic process with no friction is hence also isentropic, because for reversible, so of course no heat transfer is not enough. See, no heat transfer here. Negligible temperature gradient in heat transfer is reversible, and the no friction here. So no friction and no heat transfer. Okay, even no heat transfer for reversible process. Here no friction. Yeah, good. So I hope you can understand this. Make sure this is a very important slide. So I will. This is, yes. It is this. Delta equals 0 if the process is reversible. Okay. So this applicable, okay, for this delta S. Yes. Otherwise only delta Q0, delta S can be high if it is not reversible. Okay, good. Good. 1, 2. So that is good then. So I take this slide out. So this is complete. Okay. Madam, good morning. Lecture madam. I'm in a lecture. Okay. Afterward, I will call you. Oh. So applicability of this constant entropy processes, okay, is mainly for the isentropic. There can be compressions and there can be expansion. Okay, compression and expansion. Okay, compression and expansion. Okay, and mainly in the power plant, steam power generation, let's say in a steam turbine. So entering at 1 expands if isentropic, straight down, constant entropy, like this, 1 to 2 dash. Okay. So if not constant entropy, this will be little higher in entropy. Okay, for expansion process. Yeah, some vapor, liquid here, so the vapor turns into liquid, and vapor combination means this is a wet steam after expansion. Even if it is gas, okay, 1 to 2 straight down, 1 to 2 dash, constant entropy process. If it is not constant entropy or isentropic, so during the expansion, okay, during the expansion, the entropy can rise. Okay, so this is the constant entropy line. Constant entropy line. Constant entropy line. See, constant entropy line. But what happens is, because during the expansion, if entropy is not constant, there is little rising of entropy. There is a little rising of entropy. Yes, you can see. So your entropy after the expansion shifts. Okay, after the expansion, entropy shifts. So let me format this. Okay, entropy shifts after the expansion. Yes, very nice. Okay, entropy shifts. So if I take something like this, entropy increase, you can see 2 dashed 2. So means 1 to 2 is the standard, so actual. So isentropic is always ideal, because isentropic, you can see zero friction. Zero friction, no friction is generally not possible. Okay, so this is isentropic is ideal. Okay, ideal. Ideal. Okay, ideal. This one is not isentropic. Okay, this is not isentropic. So we would say this is non-isentropic. So this is isentropic expansion. Ideal. So this is actual. Actual. So what happens is in the actual, entropy rising. Here, yes, entropy rise, you can see. I have explained this to you, okay, earlier. Non-isentropic, but you know that entropy rises because of the friction and all. Entropy rises. You can see S2 greater than S1. This is the clausius inequality based somehow. There is always entropy increase. Yes. So ideal and actual. Same way even here. It's the same. Even for steam, you can see there is an entropy increase. See, entropy increase. You can notice this. So same way you can see here. So let me take a new slide for this. Here again, isentropic expansion, ideal. Ideal means this is not so real. Ideal means, okay, not so real. Non-isentropic, you can see here, this is non-isentropic. Okay, that is actual. But this is something not to say difficult, but this knowledge is useful. Okay, this knowledge is useful, and knowing this knowledge is extremely important. Okay, for practical application, at least you should know what to do to improve the efficiencies and all. To improve the, at least to reach this ideal isentropic conditions, because you will be dealing with this. So you will be developing this kind of solutions. Okay? You will be developing this kind of solutions. That's right. So this basic knowledge is very important. The second law is quite important. Second law is related to, actually second law of thermodynamics is about the Clausius statement and Kelvin-Planck statement. Okay, no other thing. So this is quite practical. So you have heard of energy auditing, but now people are looking into entropy auditing, not energy. Entropy is very important, means the losing of the usefulness of available thermal energy for mechanical work, the losing. Yes, we have to look into those, not only the energy balance. Not to say little too much to you, but through all these slides, I have explained you this. Okay, I have explained you this. So this understanding basic entropy knowledge is extremely important. No two words. Let me save this. Revision 2. Okay, this one. Okay, so quite practical, and it's a must to understand this. Okay, Buddha, it's a must to understand this. It's very important. So this is, you have to look into this. Beyond the equations and this practical, the real, this knowledge of entropy, somehow you have to gain this. Okay, that is very important. And a little knowledge I will put here again. This is related to okay. We talk about expansion. Expansion. We use the word actual. Okay. So here we have the word real. Real means actual. Okay. So I would change maybe this to real should be okay. Real. Okay, real and ideal. Okay, this is real. Real. Real expansion. either. Real. So ideal is the limit of the real. Of course, that is not fully achievable, but the closeness, we call it the how close real to ideal, we use the word efficiency here, isentropic efficiency. Later I will share it with you. So real expansion processes and even compression processes, I will check one for this, have a degree of friction. Generally there is a friction because this process is related to machines made of material and the friction is there. And this will generate heat, which is in effect, which affects heat transfer, so which causes heat transfer. Okay, so that's why this is related to delta Q. So non-zero delta Q. Okay, non-zero delta Q. Which means non-zero delta Q means non-zero delta Q you cannot have the equal sign. Okay, so this is not possible. This is not possible. Non-zero delta Q means you have delta S. Okay, so this is non-isentropic, hence non-isentropic. That is the case. Okay, so this is not possible. Okay, not possible to have delta S delta Q by T is not possible. So then non-isentropic means entropy rises or increases. Then the situation is this increase the entropy, make the final, yes, this enthalpy. Okay, so later we will look into this. You will know this. Is the energy level. Bigger than it would be. Okay. Yes. So enthalpy bigger. Okay. Bigger than it would be. Or else temperature bigger than it would be. So, or else it can be a gas or superheated instead of vapor. So we can discuss this afterward. Okay, we can discuss this afterward. So this is something practical. So I will mark this like here. Later we will try to understand this. So entropy increases is okay. Non-isentropic means at the end of the process, higher energy levels. Okay, yeah. So let me say this way. And this is about isentropic efficiency. Okay, this is about isentropic efficiency. Let's say efficiency in the sense deviation from the ideal isentropic process. Okay, deviation from the ideal isentropic process. This tells the efficiency. Okay, if you follow this, my notes from the beginning, carefully study, raise the questions, understand this is quite simple because I have tried to make this understanding quite naturally as possible. Okay, so it's like this. Let's say non-isentropic expansion does not deliver the maximum possible work output. Means what happens? Yeah, the working fluid after expansion some more energy is remained with no chance for a work done. So more energy remains, okay, with this working fluid. More energy remains with no chance for a work done. The working fluid after expansion, yes, more energy remains. Okay, energy is remains see, okay, the working fluid has some more energy remains, or some more energies remain with no chance for a work done. Means working fluid after work done has higher energy levels. Okay, so working fluid after work done has higher energy levels. Higher energy levels because it didn't deliver the full energy because of the entropy. So has higher energy levels because of this irreversibilities. Okay, due to irreversibilities. This and due to irreversibility and yes, due to irreversibility and heat increase, that is delta Q. Okay, due to irreversibility, that is enough for the moment. So then energy at 2 will be higher than energy at 2 dash. Higher energy means high level of temperature. See, temperature can be high. Okay. And also energy level is high, mention that. Energy levels means enthalpy, that's why. Increasing entropy makes the final enthalpy higher or bigger. See, final enthalpy big. Then it would be otherwise. Okay. And final temperature bigger. See, because, okay. Bigger. Final temperature bigger. Okay. Yes. Okay, final enthalpy can be bigger, final temperature can be bigger. Then it would be otherwise means bigger than isentropic, than if the process is isentropic. So no matter it is a gas or vapor. Okay. Otherwise, for gas and vapor. For gas or superheated vapor. Because gas means there are gas power cycles, you know that. So vapor means the vapor power cycles. So this is the situation. Okay. So at the end of the process, higher energy levels, if not isentropic. Compared to isentropic, high energy levels means higher temperatures, higher entropies. Because temperature represents the kinetic energy levels. Mainly, of course, that is for the movement of the molecules. So when it comes to enthalpy, it is more than the internal, but also the pressure levels also high. H is U plus P, we have learned this somehow. Enthalpy also a reflection of energy levels of working fluid. Good. So I hope you can understand this as well. So let me do one more. For compression, what happens if it is compression? For compression, so when you compress, okay, compress means you are doing some work, okay, on this. So isentropic means energy, yeah, you are compressing but no heat transfer to and from. So adiabatic, reversible. So when energy level rise, temperature rise, but isentropic. If non-isentropic, entropy increases the same way. If it's vapor, so the same way, like here you can see. In the compression, see the direction, temperature at the rising level, okay, it's rising level. So the entropy rise, okay, entropy rise. Here also the same. You can see the entropy rise, okay, you can see the entropy rise here for compression. Okay, compression. So you have to understand this entropy rise. Dilshan lecture එකකින් පස්සේ ගන්න dilshan. ඔව් lecture එකකින් dilshan. හරි පස්සේ ගන්න. So you should understand this. So same like, so if I compression, so let me put the expansion as well. Expansion, okay, compression and expansion. So maybe I put expansion first. Probably you are familiar with the expansion. Compression next. And compression. So instead of non-isentropic, I put efficiencies.